In Lesson 2.1, the derivative and the tangent line problem, we will begin our foray into the actual real hardcore calculus by learning about the derivative. We'll talk about what the derivative is, how to evaluate the derivative. We'll find a formula for the derivative, which we'll call the definition of derivative. And then we'll use that to find the derivative of certain functions at certain points. We'll learn that the derivative is nothing more than the slope of a tangent line of a function at a certain point generally. From there, we'll talk about how to graph derivatives given the original functions, and then we'll complete this lesson by talking about intervals where a function is continuous and differentiable. So with that, we should probably begin by talking about the definition of a derivative.
Before I show you the formula for the definition of the derivative, I would first like to tell you what the derivative is, what it represents, and how we get it. I truly believe that if you understand a formula, it will make a lot more sense, and you won't need to memorize it if you actually understand where it comes from. And so that's what this is going to be all about. So let's go ahead and begin. What is the derivative? Well, the derivative, simply put, is the rate of change of a function. Now, you've heard that term rate of change before. You've heard it in Algebra 1, Algebra 2. You've heard it 20,000 times. What is the rate of change? Well, in most of the functions that we've dealt with to this point in math, the rate of change is simply just the slope of a line. And in fact, that is the actual case. If we have a line, which let me draw one here as best I can. If we have this line, let's define 2 points on the line. Let's call this point here x comma y, or actually x1 comma y1, and let's call a point up here x sub 2 comma y sub 2. So what is the rate of change between these 2 points? Really, it's just the slope. It's the rise over run. And if we want to formalize that mathematically, we could say that the rise is just y2 minus y1, and that the run is simply x2 minus x1. Don't be surprised by this. It's just rise over run. You've seen it before in multiple ways. Here it is verbally, and here it is analytically. So rate of change is just slope if we're talking about lines. Of course, in calculus, we get away from talking about linear functions and we generalize to talking about functions maybe like this polynomial random function that I have going on over here. So my question could be, what is the rate of change of this function at this blue point? And really, how could you say? When we're talking about slope, you can say that the slope is 1/4 or that the slope is -2. But you can't say that the slope of this function is any one value. Here, the slope is going down, strongly negative. Here, the slope is going up, strongly positive. So you can't just give one number for the slope of a general function. Rather, we need to use the derivative, which is the rate of change. Now, the way we're going to do this is by constructing a series of secant lines. So we need to discuss what is a secant line. And you should already be familiar with this idea. A secant line is simply a line that passes through a function in 2 spots. So, there's a secant line right there. If I define this point as x comma f of x, and I know you wanted me to say x comma y, but we're not going to do that here. The y is determined by the function relative to x. So we'll call this x comma f of x. And that's our first point. What should we call our second point right here where we're hitting the function? Well, here's the problem. We don't know what x is. So what I'm going to tell you is that if this is our x, in order to get to our next x, which is right here, let's move an unknown amount. In fact, let's call this delta x. And what does delta x mean? Well, delta simply means change. So this is simply, I'm starting at x and I'm moving delta x. So what's my new x going to be? Don't think too hard about it. It's simply going to be x plus delta x. So that will be the x value of this point. It will be x plus delta x. And what's the y value at this point? Again, we're not going to use y. But if I simply take this as my independent variable, or my input, then my output, or my y, will simply be f of x plus delta x. Nothing spectacular there. The biggest worrisome part about this is that I'm moving delta x to get from one x to the next. So if this is x comma y, this is x plus something, and then the y is simply what I get at that new x value. So what is the slope of this secant line right here? Well, the slope of this secant line, let's see here. I'm just going to use my rate of change formula, y sub 2, and y sub 2 is nasty, but it's this. There's y sub 2 minus y sub 1. And what am I going to get on the bottom? Well, it's going to be my x sub 2 minus my x sub 1. So that is going to be my rate of change of this secant line. Now, how does that help us? Or actually, can this be simplified? Clearly, I'm sure as soon as I wrote it, you noticed that I have an x and a minus x here. So let's just go ahead and get rid of those. Those cancel each other out, and we don't really need this plus sign here. So right here is our rate of change of that secant line. In fact, that's the rate of change of any secant line that I can draw. So long as I know what x and delta x are, I can do this. In fact, let me draw another secant line that's a little bit closer to what we would expect here. Let me draw a secant line going through this point. You see that I've just made my delta x a lot smaller now. This now is my length of delta x. Delta x got a lot smaller. So what's going to happen to my derivative, my rate of change? It's going to become much closer to what my actual rate of change is. And if I draw another secant line, bringing it even closer still, I can draw multiple secant lines, and eventually what's going to happen is that delta x is going to be reduced so much that I have 2 points that are almost on top of each other. And that is a tangent line. A tangent line is simply a secant line, but it only hits the function at 1 point. Only at 1 point rather than 2. Think about the 2 points coming together, and once they do that, I've approached my tangent line. So what is the rate of change, or the derivative, of this tangent line? Well, a lot of times we write the derivative as f prime of x. So you'll get used to that as we go throughout the year. F prime of x is the standard way of writing the derivative. But we define it, as I said, we want that delta x to come to 0. But look at this function that we wrote right here. What would happen to this function if delta x were equal to 0? What would happen? Well, clearly I'd have a 0 in the denominator, and that's no good. So delta x cannot be 0. However, what I can do is I can explore the limit of that function as delta x approaches 0. And that is going to give me the definition of a derivative. This is a formula that you've probably seen before. You probably worked with this formula in pre-calculus, although you didn't know it held any special relevance at that point. Now you do. This right here is the definition of derivative. Definitely write it in your box there on your note sheet. It's going to take a lot of work to get used to it. But once you get used to it, it's not that bad of a function. It just looks bad. But that is the definition of a derivative. And now that we know that, why don't we try some applications of it, plugging in numbers and seeing what we get for the derivative of certain functions. We'll begin with example A. In examples A and B, we are to find the derivative of the given function using the definition of the derivative. And following from that, we are to find the slope of the tangent line to the function at the point that's given to us in the example. So if we take a look at example A, you can see that we have this linear function, f of x equals negative 2x minus 4. Without even doing this problem, you should know what the derivative is at every point along this line. Because remember, derivative is kind of like slope. So anyway, let's say you didn't know that. And let's say we want to work this out. We'll start with f prime of x. That's usually how we refer to the derivative. Don't forget your limit as delta x approaches 0. Many times people forget that and it really messes them up. Now, for this first part, the f of x plus delta x, all we need to do is take x plus delta x and feed it into the function f. If we do that in this case, we'll have negative 2. Instead of x, we'll have x plus delta x, and then minus 4. So that's the first part of our formula. The second part of our formula, this minus f of x, that's nothing more than just subtracting the original function. So there is our numerator, no big deal. The denominator, of course, is just delta x. So from here, you need to do a little bit of distributing, some combining of like terms, cancel things out, all that stuff. I'm not going to do the algebra here because I assume you can do the algebra yourself, being as how you are now taking calculus. If you need to pause the video, go right ahead. But be sure to come back when you have completed all the algebra on this problem. If you do it correctly, you should end up with something along the lines of the limit as delta x approaches 0 of negative 2 delta x over delta x. Of course, if you plug the 0 in, you'll have 0 over 0. We spent a lot of time in Chapter 1 talking about how terrible of a thing that is and how awful and bad. So let's just go ahead and cancel these out. And now, if we plug in delta x, well, there's really nowhere to plug in delta x. And so what we get is that the derivative of this function is negative 2. Interesting. There's no x. It doesn't matter what x is, the derivative of this function is going to be negative 2. Or, if I want to write it a little bit clearer, I'll write that the derivative equals negative 2 for all values of x that are members of the real number set. Stated in English, for all values of x, the derivative is negative 2. So let's move on to the second part of this example. What is the derivative at the point 1 comma negative 6? Well, all you need to do is just plug 1 in for x. And there is no x. So there we go. The derivative of this function at 1, at x equals 1, remember that's where we're looking, is simply equal to negative 2. Go ahead and graph it. See if it seems right to you. When you graph it, you're going to get a line. That line has a slope of negative 2. And so the derivative of that line at the point 1 comma negative 6 is negative 2. No big deal. So let's move on to an example that actually does have us doing math. In example B, we'll take a look at a second degree polynomial here, and it'll be a lot more fun and exciting than example A. In example B, we have this quadratic function of t. So don't be alarmed, I've changed up the definition of the derivative to reflect the fact that we're dealing with a t now. Nothing changes. X, t, whatever you want to call it, they're all independent variables in this case, so no big deal. Now before we begin this problem, I have gone ahead and graphed for you the function f of t. This is t squared minus 12t. And we're trying to find the derivative of this function at the point 6 comma negative 36. In other words, we're trying to find the slope of the tangent line right here. So before we even begin, go ahead and take a guess what you think it might be. Alright, hopefully you have your guess. And with that, let's go ahead and see what this is going to look like. If I plug t plus delta t into f of t and work on finding the derivative, it's going to look something like this. I will write t plus delta t quantity squared minus 12 quantity t plus delta t. That's simply the first part of the definition of a derivative, and then I'll just subtract my original function, t squared minus 12t. Of course, in the denominator, I will still just have delta t. So to do this correctly, you're going to have to square this binomial, distribute this scalar multiple, combine all these like terms, do all this crazy stuff. So certainly you should pause the video and give that a shot. As for me, I've actually already done this one. So when you come back, let's see if you get what I got, which in this case is delta t squared plus 2t delta t, and then minus 12 delta t. That's what I got when I simplified the numerator. The denominator didn't change, it's still delta t. So what can I do now? Of course, I forgot my limits, even though I said earlier that that was extremely important, and you should not forget them. But if I put them in now, can I simply plug 0 in for delta t? I'll have a 0, 0, 0 on top, I'll have a 0 on bottom. Clearly that's not going to work, but in this particular case, I can factor out and cancel one of those delta t's. So what I'm going to end up with is delta t plus 2t minus 12. And that's simply by scratching this out, and this out, all those canceling with that. So you see where that comes from. And of course, what did I forget again? My limit. Please do not forget your limits. Do not forget your limits. All right. Well, if I plug my delta t, if I plug 0 in for my delta t, what am I going to get here? My derivative, it looks like I'm going to get, well, 2t minus 12. So that is my derivative of this function. If I know what t is, I can just plug it into that derivative and it will tell me the slope of the tangent line at that point. So let's take a look at this blue point right here. If I draw a tangent line, and I'm not very good at drawing lines on the computer, but it would look something like that. What does the slope of this line appear to be? Right, I don't know either. No idea at all. But if we find the derivative of the function at that point, and again, that is where t is 6. So f prime of 6, if I run that through this equation, that's 2 times 6 minus 12. Clearly that gives me 0. Oh, and sure enough, the slope of this tangent line is in fact 0. So that's how the derivative is used analytically. That's how we come up with a function that represents all the slopes of all the tangent lines of that function, and that's how I can use that derivative to find the specific slope of the tangent line that I'm looking for. So we can do a million examples of just plugging in x plus delta x and all this good stuff, all these delta x's and limits. But rather than keep harshing up on this one, let's go ahead and take a look at just doing this graphically without any functions at all. Let's see if we can work this out using our knowledge. In examples C and D, we aren't given the actual function, so we're not going to be able to actually find what the derivative function of these are, but we can use the graph to try to sketch the graph of the derivative. If you remember, the derivative is simply the slope of a tangent line. So what we're going to do is we're going to create a graph of all the slopes of all the tangent lines across the entire function that we're given. Let's start with example C. If you take a look at example C, if we start any place on this line, I'm going to start right here. What is the slope of the tangent line to this function at this point? Well, the function itself is linear, and so you should be able to tell that the slope right here is negative 1. And so I'm going to put a dot down here. This will be my derivative function, and the derivative here is negative 1. Let's jump to somewhere else on this graph. Let's look right here. What is the derivative of the function at this place? Well, it's also negative 1. In fact, no matter where on this graph we go, it appears that the derivative is going to be negative 1, no matter where. So what is the graph of our derivative going to look like? It's going to be a horizontal line at y equals negative 1. No matter where on the graph we go, the derivative, the slope, is negative 1. And so there is a graph of the derivative of our original function. That wasn't too difficult to figure out because it was a linear function. No tricks to that one. However, when we take a look at D, here we have what appears to be a sinusoidal function, and you know, if it is sinusoidal, of course, we could start with y equals sine of x, and we can plug all of our stuff into this. Watch how ugly this looks. If we do this, we're going to get the sine of x plus delta x minus the sine of x all over delta x. And we can't distribute sine, so I'm not really sure how we would do this. just yet. We will learn that later, of course. But if we're just looking at the graph, do you see anywhere on this sinusoidal graph where it appears the slope of the tangent line would be 0? Well, right here, if we were to draw a tangent line, the slope would be 0. And right here, if we drew a tangent line, or here, or here, all of these places, the tangent lines appear to have a slope of 0. And so what I'm going to do is for the graph of our derivative, all these x values, the derivative is 0. So that gets us a good start. Would it be okay now to just draw a straight line here? Clearly no, because along this graph there are places where it is sloping up and places where it is sloping down, so we need to account for that. In fact, if we take a look at the interval between here and here, what's happening to this graph? And hopefully you realize that this graph is going down the entire time. And so that means that our derivative is going to have to be negative this whole time. Furthermore, it appears that our biggest negative slope, largest negative between here and here, is going to occur at about negative 3 point, if I look carefully, I would guess negative 3.14159 maybe? Just a guess, I don't know. But that appears to be our largest negative slope. And in fact, we'll learn later that the slope at that point actually is negative 1. So if I put that down there, now I can draw the derivative in that interval. The derivative is negative the entire time, which corresponds to the graph decreasing in that interval. And there you go. So what's going to happen in the next interval from here to here? What's the graph doing? Well, clearly it's going up. It's increasing. The slope is positive. And for that reason, it seems to have the biggest positive slope right there. And so that appears to be the graph of the derivative during that interval. And we'll just finish this up and realize that the derivative is negative on this last interval. So that's interesting. A sinusoidal function appears to have a sinusoidal derivative of sorts. In fact, if you look at this blue graph that we've drawn, while it is sinusoidal, it appears to represent a certain type of sinusoidal function. In this case, it looks to be y equals cosine x. We'll learn later that that is the actual truth. The derivative of sine is, in fact, cosine. That will come later on, but now you see why that will be the case when we get there. So given a graph, if you want to draw a graph of its derivative, start by finding all the places on the original graph that have a derivative of 0. And then just try to figure out what happens in between those 0 points. Is the graph going up? Then the derivative is positive. Is the graph going down? Then the derivative is negative. And you can kind of fill in the blanks from there. So, given all that, let's take a look at 3 more examples on which we're going to try to determine on which intervals the graph is both continuous and also where the graph is differentiable. In other words, where it actually has a derivative. Let's take a look. Before we get into these last 3 examples, it's important that we revisit the definitions of continuity and talk about how we know where a function is differentiable, in other words, where we can do the derivative. Remember that continuity simply means that the limit of the function from the left of some function is equal to the limit of that function as we approach whatever value from the right. So long as that happens, it is continuous. That being said, if we take a look at this function right here, where is it continuous? Well, it looks like it's continuous everywhere except at its asymptote. So the way we could say that is negative infinity to positive 2, and we can join that with the union of 2 to positive infinity is one way we could write it. We could also write that it's continuous for all x's that are a member of the set of real numbers except for where x equals 2. Anywhere else it's continuous. If you want to use the working definition of continuity, I can draw this graph without lifting my pen or pencil, except at where x equals 2. There appears to be an asymptote. So let's talk about differentiability. Differentiability essentially means, and I'm going to draw this down here, that the limit as we approach from the left of the derivative is the same as the limit as we approach from the right of the derivative. So you can see that it's very much related to continuity, except we're dealing with the derivative now. Where does this function seem to break its differentiability? Where can we not find the slope of a tangent line? Well, if you look carefully, there's really only one place in the graph that a tangent line fails to exist, and again, that is at the asymptote. So this function is differentiable, again, for all x's in its domain, or rather for all x's that are real numbers, except for where x equals 2. So in this particular example, the intervals of differentiability are the same as the intervals for continuity. But is that always the case? To answer that, let's take a look at example F. So example F appears to have a node on it right here at this corner. Is that going to break our continuity or our differentiability? Well, look back at the definitions of continuity and differentiability that we just did in example E. Is the limit from the left and the right the same for everywhere on this graph? And I hope you'll agree with me when I say that, yes, that is the case. Even at the node, the limit from the left appears to be 3, while the limit from the right appears to be 3. So this particular function is continuous for all x's that are a set of real numbers. However, as far as differentiability is concerned, things might be a little bit different. On the interval from negative infinity up to positive 4, what would be the derivative here? Hopefully it's clear to you that the derivative on this interval is positive 1. There is a slope of 1 as we go here. However, the derivative on this interval from 4 to infinity appears to be negative 1. The function is going down now. So what happens at 4? Well, the limit of the derivative from the left is not equal to the limit of the derivative from the right. And so this function is differentiable for all x's except the x that represents the node, x equals 4. Of course, you could also write this in interval notation. That's also accepted, no problem. But the important thing to remember here is that a function does not have a derivative when there is a node, or alternately when there's a cusp, which would look something like this or like this. It's a very similar concept. The limit of the derivative from the left is not equal to the limit of the derivative from the right. So nodes and cusps, no derivatives. Of course, we saw in example E that there is also no derivative where there is a vertical asymptote. That should be clearly evident. And with that, let's take a look at our last example, example G, and see what happens with a good tangent function. And so for our last example dealing with continuity and differentiability, we're going to take a look at this tangent function. Now let's go ahead and begin with the continuity of it. And if you look clearly, it is continuous except where there appears to be these vertical asymptotes. And of course from pre-calculus, you do know about the vertical asymptotes. They occur at pi over 2, 3 pi over 2, 5 pi over 2, all of those odd pi's over 2. So what we can say is that this function is in fact continuous for all x's except where x is equal to pi over 2, 3 pi over 2, 5 pi over 2. How many of these are there? How many asymptotes are there? Way too many to list. So perhaps what we should say, rather than this, is that this function is continuous for all x's except where x equals pi over 2 plus or minus pi n. And of course, this is where n is a member of the set of integers. So, there we go. That defines our asymptotes, which helps to define our continuity. Now, if we talk about differentiability, anywhere that the graph seems to exist, the derivative appears to be smooth. There's none of these going up and then all of a sudden reversing course and going down. No jerky motions, no cusps like we talked about, none of that. So this is in fact differentiable for all x's that are on the domain. Or if you wish to write it out some, we could say all x's that are in the set of real numbers except for where the asymptotes are. Of course, I'm just rewriting what I have above just for the sake of brevity. So, there we go. Continuity is simply where the limit of the function from the left and right approach the same thing, and differentiability is simply where the derivative from the left and the derivative from the right approach the same thing. Remember that there are three ways that derivatives don't exist. And let's see, three ways derivatives don't exist, and you should be able to write this out before I get to. But one, if there is a vertical asymptote, and of course we know how to find those. Two, if there is a node, that's like the absolute value function could rise to a hill or could drop to a valley. And then the third, similar to the node, is if there is a cusp. And we'll see those a lot of times when we deal with fractional exponents. But that will come later, so we don't need to worry about that for now. So, this has been a very important lesson. In this lesson, we've defined and worked with derivatives. We've related them to slopes of linear functions, and in fact, we've looked at secants and tangents, which themselves are lines. We've talked about how the derivative at a certain point in a function is simply the slope of the tangent line to the function at that point. From there, we took a look at some graphs, talked about how to find the derivative graph of an original function, and we concluded this lesson by talking about continuity and differentiability. Make sure you remember all these things as you progress through your homework tonight. It's not an easy one, not a quick one, but it is doable, and you will hopefully get a lot out of it. And so, on your homework, good luck.